Yeah, I think he told me. Yeah, 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 yeah. I think Hari also wrote. Yeah, that. Yeah, he was visiting. Do you want to visit concurrently? Sure.
Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at DEC and RBCTPS, DAC. It's my pleasure to introduce today's speaker, Professor Dinesh Bharadia, and he will be speaking on empowering AI-based real-time intelligent control, optimization, and security in next-gen networks. Dinesh Bharadia has been an associate professor in the EdgeRIC department at the University of California, San Diego since July 2020, where he did extraordinary WCSNT. He received early promotion to his tenure professorship and held assistant professorship for 4 years from 2018 to 2022. He received his PhD from Stanford University in 2016 and was a postdoctoral associate at MIT. Specifically, he built a prototype of radio that evaluated the long and resolution wireless that radios cannot transmit and receive simultaneously from the same frequency, which inspired research on this topic from different communities. From 2013 to 2015, he worked to commercialize his research on full duplex radios, building a product that went successful field trials at a tier 1 network providers worldwide and SA Telecom. He serves as a technical advisor for multiple startups. He was named to Forbes 30 under 30 for the science category gold medalist in the recognition of his work. He was named a Marconi Scholar.
I think he good.
Outstanding wireless research and was awarded with the Michael Simulation Award. The MIT Technology Review also named him among the top 25 innovators under 35 worldwide in 2016. The UPSC, his group WCSNT designs and prototypes systems for wireless communication, computing, networking, and sensor design with applications to privacy, security, robotics, health, and engineering. Much of the group's research has inspired from the new research areas for modern communities like communication theory, circuits, RFIC, and robotics. We request the audience to keep your microphones on silent for the duration of the talk, except when asking questions and for questions, please feel free to ask and unmute yourself. And so or type them in the chat box. Over to you.
Thank you. Yeah, I think sort of long introduction for, I guess, learning next time not to write a short, long bio. But okay, so I think this is a joint work with Srinivas Shakotai at TAMU. And I think lots of students and collaborators have contributed to this, right? So I think what happens is every time somebody picks up something, we add an additional adjective, right? Control, optimization, security, and I don't know what someday this title might go out of, yeah, the slide itself, right? So, okay, so with that, let's take a look at what's going on with the wireless as such, right? So there is something called Open RAN, right? And the idea of this Open RAN has been that it's sort of supposed to get similar to what happened to the, let's say, the uh, PC design, right? You sort of got different vendors, you agreed on certain specs, right? You put today when you build a PC, you buy something from somewhere, motherboard from one person, right? RAMs from different person, right? And other things from different person, and then you can put together whatever configurations you want, and you try different configurations and so on and so forth. Something similar is what I think Open RAN is supposed to provide, right? All these nice uh, multi-vendor, low cost of ownership, right? So much, right? I think whatever you imagine today with PC, it's exactly what they were hoping will happen with 5G, right? So, and this is where even the expectations were like from ABI research, right? Look, by 2030, right, 50% or more would be at least driven by the Open RAN, right? I don't think that's happening as much as fast, right? Okay, I think still the latest and the greatest is Ericsson's deal with AT&T, where Ericsson agreed to use the radio part from somebody else instead of they designing their own radio. That's all it is, right? It's still everything above radio still is their own RAN stack, right? So it's the step in the right direction, but not yet fully there, right? I think yesterday's discussion with some of the key vendors in India, I think, and so far my 3 weeks visit, it seems like India might take the leadership on doing Open RAN deployments than anybody else, right? So okay, so this is great about Open RAN. Now, what is it that we want to do with the NextG? So the interesting thought process with NextG is that we want to empower networks which are purpose built, meaning you build a specific network for different use case, right? Smart manufacturing to smart warehouse to whatever smart you want to build, right? You want to build networking, which essentially is a solutions product, not just a networking, right? It's a mechanism to impart an entire solution and it's digitalization and therefore sort of delivering these requirements, right? And these are prominent use cases you see around when you go read standards and other things, right? They want to do low latency, high reliability for autonomous vehicles, right? This is slow to take off, right? There is a lot of AR, VR use cases which are also springing up. I think in specific, my bet at this point is on, I don't know if you have seen these Meta Ray-Ban glasses. I think those seem like more functional use cases at this point. You have a glass, it has a button on it, right? And you can take a photo and it can do a bunch of basic things, which is it does relatively well, right? I think that to me seems a much more pliable, which will take place, right? But the problem with all these is that these different types of devices and ecosystems and the networks designed for specific use cases and deployments would have very diverse requirement, right? And this Open RAN came along, right? And we were super excited to see, hey, can I deliver video with high quality of user experience, right? Instead of focusing on quality of service, right? I think for the longest time, networks and network designer have focused on designing quality of service, right? So we stepped out with a goal of, hey, can we do a quality of experience optimization? And in the process of that, can we do it on top of an Open RAN, right? That was really where the thesis when we started this work, right? And towards that, let me just give you, sorry, this is a bit slow somehow. Maybe some interference. Okay. So let me take an analogy for Open RAN, right? This is what it was supposed to, right? In a phone ecosystem, right? We have lots of hardware people, OnePlus, Xiaomi, and so on and so forth, right? And then we have these operating systems provider, Android and iOS, and they essentially abstract out all of this hardware into some functionality of APIs, right? These are the operating systems, right? And then on top of those, we have built all these apps, and these apps have truly enabled a new e-commerce. All of the commerce today we see is sort of sits on these apps, right? And it sort of has made everybody in this ecosystem very powerful and rich, right? Okay. Now the same applies to the world of 5G, 6G, or the hope is that it will apply to the 5G, 6G, right? So here are 2, 3 things we want to do, right? We want to deliver intelligence and automation, right, into the world of RANs, right? Okay. And there is a way to do it similar to this ecosystem. And I'll explain this, right? So this is what a traditional RAN architecture looks like, right? Again, it's the more 5G version. You have a radio, which is essentially a tower on which the radio, sometimes with lots of antennas, right, sits. This connects to the ODU, which I think in just broad sense saying L1 to L3 for the 5G sits on this side, right? Essentially PHY layer, MAC layer, RLC, right? And then OCU sort of close to the cloud, right? As I start drawing these clouds, all of these are supposed to be in the cloud, core network and everything else along with this, right? So this becomes like, think of this as your PC hardware, right? Okay, for the world of ORAN, right? Okay, buying motherboards and everything else from different people and then putting it together, right? This sort of becomes now the operating system. The non-real-time RIC and near real-time RIC are sort of the RICs, or these are the operating systems which are proposed to potentially deploy different apps on them, right? So think of them as iOS/Android, right? The difference here is the time scale at which these operates, right? Okay. Now you could potentially develop different apps as you go build purpose-built networks, right? And by using these apps, you can tinker the networks and do these optimization, right? Now, all this is great, right? And now what the hope is that these parts will come from different vendors, different people will provide operating systems. Overall, it will create a both economic and a large scale sort of ecosystem, right? Of people doing different things, right? Okay. And just to give a sense, right? This is what I guess has been standardized. Here are the time scale for these optimizations, right? So you have near real-time RIC and non-real-time RIC. Near real-time RIC is supposed to do optimizations on the order of tens of milliseconds to a second, right? So often this near real-time RIC is also deployed in the cloud, right? Now, 10 millisecond in the world of wireless is a long, long time, right? It's like million sort of time of events which has taken place in 10 millisecond, right? And I'll explain that with a more concrete example, right? So what it means is that you can use this near real-time RIC largely for macro level optimizations, right? You cannot do fine-grained optimizations with this near real-time RIC, or at least that was our thesis, right? And here's what inspired this thesis, right? Again, I think it's very straightforward, and once you see it, you will also agree, right? So this is how typical deployment takes place. You have these multiple towers. These connects to one ODU, right? And this ODU, well, it has to be less than 100 microsecond from towers, right? So it cannot be very far away, right? Maybe a few kilometers from this, right? But then this cloud slash OCU and OCN and all of those cloud elements, they are literally miles and miles away from this ODU, right? And often the expectation, right? Much like what happened in SDN, right? We wanted to do software defined networking, and most of that software defined networking was done cloud managed, right? All of it is still cloud managed, right? So people thought, let's just have a central sort of intelligence which will intelligently sort of tune and optimize the entire network, right? And that is the philosophy. And it's a good philosophy because it makes it easy. If something is centrally deployed at a single cloud, it's easier to deploy that and therefore manage it and so on and so forth, right? The problem with the wireless is this, right? You have events which are high mobility, which is what you didn't have in the world of SDN, right? Software defined networking was great because networking and overall wired networking, the events didn't change as fast. Wireless is a different sort of problem of its own, right? Okay. This is where the problem lies, right? If you have a train, you have coherence time of 0.6 milliseconds. Again, these are theoretical expectations, right? In practice, they can be much faster, right? Even car moving at 13 meters per second has just coherence time of 2 milliseconds. So imagine you sending some information back to the cloud, which takes 5 milliseconds. Let's say you took instantly decision and sent the decision back. Even after doing all of this, your decision will be at least operating on 10 millisecond delayed scale, right? Which for most of these use cases does not make sense. So this is where our thesis number one, right? We need RICs or RAN intelligent controllers, which can support these dynamic mobile links. Okay. So thesis number one, we need to have something which is more real time, which is attached to the DUs, close to the DUs, and can programmatically provide decisions to different RUs and do the necessary optimization. We call it real-time RAN intelligent controller. The precise point here is deploy some form of edge intelligence, right? Okay, which can take information at very short time scales, and instead of trying to predict what would happen in the future at 10-20 milliseconds, instantly provide decisions back so that you can optimize the network and provide different services, right? Now, the second key element when we were designing this, right, we were actually trying to build some video QoE optimization, as I was telling earlier, right? So to build this video QoE optimization, right, we need to understand video and its state, right? Quality of experience and quality of service are two different things. Quality of service is network providers attempt at, okay, you need this much data rate and this much latency. That's your estimate for quality of service, right? And how do you get those numbers? Nobody knows, right? I think they do broad scale approximation. Let me give an example. You have a video of a slow moving event, right? Okay. And you have a video of a car which is going at a very high speed, right? Okay. Or you're just playing Fast and Furious or watching Fast and Furious, or you're playing some NFS, right? We used to play NFS. I don't know if it's anymore there, right? Okay. But just you're trying to have this gaming of NFS, right? These three are just video contents. And here is what is different about them. If you said you have 1 megabit bitrate to provide for all these three videos, there is something called index called VMAF. I'm not sure if everybody knows, but it's sort of a quality of experience metric which Netflix has defined. And for these three different videos with 1 megabit, you achieve different VMAF scores. So higher the VMAF score, the better is what you're sort of building. So if you have 40%, that's good. But if you have 70%, that's great. So these videos, which are just different content, with 1 megabit can provide different VMAP from 80 to 40. So if you as a provider provide a broad stroke policy that I'm going to just do 1 megabit for all videos, right? You will provide different quality of experience to each user. So you need to rely and get some application awareness into the RAN stack. This has been really, really hard to get the application awareness, and it's very hard to standardize. And the market itself, or the economics of the market also, people don't want to share these information, right? And don't ask me why. I have talked to YouTubes and the Netflix of the world to share these information with the RAN. They don't trust each other, right? And they do funny things with each other, right? So that they are just trying to gain the market economics. So I think that said aside, what we want is somehow an awareness of what the application state is into the RAN, and then use that application awareness to do RAN optimization. So this was the second pillar for what we were trying to do, right? So how do we bring application awareness into the user prioritizing and scheduling in real time, right? So this is where I guess the solution basically is very simple, is to somehow build application awareness. And it's a more of a systems problem than actually sort of. So let me just explain how this is the final system. So we saw these parts earlier. We have real-time RAN intelligent controller, the EdgeRIC, right? Okay, and we saw the near real-time and non-real-time RIC. There is an application server. We try to get application state through a Redis database, which essentially takes the E2 interface. Again, lots of interfaces. This is just how you make things ORAN compliant. Don't get bogged in these details. The more important point is that the application server sends us this state. This states then translates back into the EdgeRIC, and it was also provided to other RAN intelligent controllers as well. So first, we enable for the first time an application awareness across all the RAN intelligent controllers, right? It's sort of like, think of in the world of app ecosystem, we are sort of giving operating system a new feature of its own. So we build this new operating system. In addition to that, all the existing operating systems were empowered by getting application state. That's second point. Second, and then we built some real-time information exchange and sort of built EdgeRIC on top of those real-time information exchange. And you as a user can write micro apps. So by the way, if you go today to edgeric.github.io, you can download all of this software and you can start writing your own micro apps and do ML, AI, whatever you want for the entirety of the 5G, 6G, right? So first, our platform is application aware. It can handle dynamic environment changes in real time because of this real time exchange, right? We have built the entire infrastructure so that this exchange of information takes microseconds, okay? And finally, we are close to standards compliant. Okay, it's not fully compliant. I wouldn't say that, right? It's close to there, right? And lots of things we do are very, very lots of optimization, which I think required us to. And sometimes we get some additional fields from the RAN stack because we have open source RAN, so we can do whatever we want, right? But to large extent, we have followed some compatibility standardization. And at some level, there is an activity right now in NGRG on pushing real time RAN intelligent controller called DApp slash something along those lines, right? Okay. So I'm going to first answer a question with give you with results, right? Like, this is always a question I get, right? Hey, Dinesh, there is near real time RAN intelligent controller. You argued we need EdgeRIC, right? Because of some of your hypothesis, right? Is it even true? So I'm going to give you quick results, right? First is, can we improve throughput with EdgeRIC, right? Instead of making decisions with near real time RIC, if I were to do it things with EdgeRIC, I get good improvement. From 20, I go to 30. Good, 50% improvement, but throughput is throughput, right? Like, why do we care, right? Okay, maybe it is useful, right? Here is a more scientifically interesting thing for me, that something you train as a reinforcement learning model to do throughput optimization versus something you train in near RT RIC. You see, in near RT RIC, you have the model is not training, it's actually fluctuating. And if you point the model or plot the policy of this model, what is learned at these points, you already see there is an instability, and it's sort of doing the delay in the decision making is hurting the model's training entirely. Okay, right? I'm gonna just show you some initial result to show what we are possible, right? Finally, we took application awareness, and what if the media buffer, let's say you watch a YouTube video, right? You have a certain amount of media buffer, right? If I know that knowledge of media buffer, right? can I use that media buffer knowledge to provide you better quality of experience, right? And here is the stall duration. We show with our reinforcement learning model, we can reduce those by 90% compared to the max weight and max EQI schedule. Yeah, go ahead. So in this, yeah, so I think I'll get to that, right? But in rough context for this specific context, uh, your video buffer you have on your phone, right? Let's say you have half second of video buffer, he has 1 second of video buffer. That is application state for us at this point in time for this application, right? So application server telling us this particular client has this application, this much video buffer, that much video buffer. So an example of this is following. So imagine you are going to go into a deep fade, okay? Because your channel is getting worse, right? And you have a very, very small amount of buffer, okay? Like a small amount of like 10 millisecond more video buffer left for you to watch. Now, RAN's traditional optimization strategy would be, okay, I want to maximize throughput or the network capacity overall I deliver. So it doesn't make sense for RAN to give you any more resource block, okay? Because you are on a deep fade, giving you more resource block is only going to get very small amount of throughput on those resource block. So strategy is to give everybody else, Anurag and Chandra, more slots, right? For some reason, okay? This is because we didn't, when you don't have awareness, you would do this. But as soon as somebody tells me application awareness, right? That, hey, his buffer is about to run out. Even if he has a deep fade, you should give him more resource blocks so that he has enough buffer when he goes into deep fade and comes back out, he would at least sustain all of that. So this is what application awareness means in this context, right? That can I give this awareness to the scheduler about his buffering state so that he can be provided with more slots so that he can sustain and have a minimal stalls of videos, right? So that's what I mean by, and again, look, this is just for video. This is what we define. You have to take every application and define that for that application, or application provider has to make that definition, and he has to then exchange that information as well to us, right? Okay, and provide that, right? So now, yeah. So this is the closest. Sorry, there is only one near RTRIC, right? Okay. Right. Oh, I see, I see, I see. This is, I think we created our own variant, right? Okay. But you can think it's close to OSC RIC. Okay. Now we are testing the same thing with OSC RIC, right? Because we mostly have been using SRS RAN and building everything on top of SRS RAN. So SRS RAN right now has compatibility and set up with both FlexRIC and now, or they also support OSC RIC as well. So that's what we tested against. Yeah. Yes. So I will go into the details now. Okay. Give me 4 minutes, right? And I will get to your questions, right? So, okay. So this is where we started off, right? Building EdgeRIC. Since then, we have been building lots of security MIMO apps as well, right? Where we are doing anti-jamming, jamming, and so on and so forth, right? We have been doing energy optimizations, which antennas to turn off, which antennas to turn on, right? And sort of saving the energies on the base stations, right? And then how do we build purpose-built networks for delivering AI, right? So for example, you're running like chat GPTs and whatnot, right? And if you imagine you have a local instantiation of your chat GPT, how do we build networks which can be giving you seamless experience for your AI related queries and so on and so forth, right? So again, these are some of the things we are right now working on, right? Okay. So I'm going to get into the details of what I showed you the results, right? How did we get those results, right? How did we build EdgeRIC, right? So in order to cover the breadth, I may go a little bit fast for the rest of the concepts, right? Okay. And if you want more details, I can pinpoint you to the paper, and feel free to ask that question as well, right? Client, which is giving the rebuffering state. So these become part of the environment. So this is your entire wireless channels and everything, plus your application client. So RAN gives the RAN state, application gives the application state. We have built EdgeRIC, where EdgeRIC has OpenAI Gym. I don't know if everybody knows OpenAI Gym, but it's just a fancy way of doing a lot of AI things and working with them very, very seamlessly. So we integrate with OpenAI Gym so that whatever apps you write, they can directly be using ML AI natively, and then you can send actions back to the RAN stack for RAN stack optimization. Okay. So this is what I defined as environment. Now, all these RAN state also is sent to Redis database, right? Which continuously logs all the channels, all the states, and this information is also then shared with near real-time RIC so that it can do new policy training. So imagine you deployed a reinforcement learning model here, but you want to continuously train this model parallelly in the background as well. So you do all the training of that model in near real-time RIC. Yeah. So this part sits right next to the DU. This part is in the cloud. Yeah. Yes. It's 100 microsecond. That's a requirement, 3GPP requirement, 100 microsecond. So is that so? So RU to DU, this connection always has to be less than 100 microsecond. Otherwise, your decoding and everything else and the hi-fi, everything fails here. Okay. And our latencies, and I will get to that, right? And this is where EdgeRIC has to sit right here itself, right? Okay. So what do, you just have to take your RAN stack and patch it to support EdgeRIC, and then we have our EdgeRIC, it automatically controls and starts doing everything you need it to do, right? Uh, yes, I will. Let me get into more details, and then as I get into more details, I can come to this, right? So, yeah, right, right. So, yeah, yes, yes, yes. So RAN is running a traditionally what they run is called proportional fairness. Many RANs actually run proportional fairness, right? And then they try, actually this insight came from talking to a lot of RAN vendors, right? And everybody, at least we understood, and this is more of a commercial RAN vendors, right? Capgemini and several others out there, right? Radisys and several others. They definitely support proportionally fair scheduler, and they have weights which they in some form manage and change. And anybody who takes a reference design from these guys, often enough, they are trying to play with these parameters of weights so that they make their own customized design as they want, right? So this is a great, simple, and proportionally fair scheduler. The great thing about it is that it can be modified to do anything you want, right? You can choose weights in a way that it becomes max CQI to max weight on one side, and you can easily do all these things, right? And actually, I think Srinivas has a very interesting paper where he argued that if we did a direct RB allocation, right, in the RAN, or imagine EdgeRIC took all these RAN state information and it came back with decisions of directly the resource block assigned to which users and MCS and everything else assigned associated with it, right? That while we thought was interesting, it's not as easily deployable, right? And therefore we went to the weights. But Srinivas did, I guess, explain to me once that even if we did direct resource block allocation or if we just did weights, you can achieve the same result. So this is actually an interesting result. You don't have to do direct RB allocation, just do weights and you'll get the same outcome which you would get by allocating RBs. Okay, moving on. So the goal here is now, can we do QoE optimization, right, with this? Give me 1 second. I think the clicker has, yesterday also it had some issues. Okay, now it's working. Okay, so I have skipped the details of how we built EdgeRIC for primarily just a lot more software engineering and sort of details of it. Again, the code base is available online if you want to write. I'm just going to show you in one time slot, right? This is the unit of time slot in the world of RAN is called TTI, right? So in one TTI, if I have 90 users and if I want to send the state of the 90 users for a bandwidth of 20 megahertz, I can easily do that in less than 50 microsecond. So EdgeRIC was built in some specialized way in software engineering, but this allowed us to get very, very low latencies. Just to give you a context, prior efforts trying to build, they were barely getting less than a millisecond, or millisecond was the best they could do. We basically took apart the stack, understood where the bottlenecks are, redesigned the entire stack, or not the stack, but the way to transport these things so that it's extremely energy efficient, sorry, latency efficient, right? And this shows overall the latency is less than 40 to 50 microsecond on medium. On 90th or 99th percentile is close to 60th microsecond, 60 microseconds. So it's extremely, extremely fast. 60 microsecond information going from here to here is really, really good. And this is not like any specialized processor or just standard x86. Yeah, socket based 0MQ implementation. Yeah. Sorry, good. Yeah, 0MQ is the way to implement all of this, right? And there is some special form, or over time we have been sort of doing combination of ZMQ, that's the 0MQ, plus shared memory, plus some L2, L3 caching now we are exploring as well, and how we can use those in a combined form. Yeah.
So is it for how many user requests? The number of user requests.
So good point. Good point. So in real life, what happens is that in one time slot, you almost always only have 5 to 6 users in that 1 millisecond to share that RAN state to those 5, 6 users. And if you do overpacking and everything, then you will maybe get to 30, 40 users. So we are already doing 100 users or 90 users in one TTI. So just to example, right, in one base station at one cell site with one sort of direction, this translates to 90 times 1,000, 90,000 UEs in 1 second you can accommodate. So just to give you 90,000 in 1 second, you're serving to that many people, right? Which is, I think, a rare event. These base stations have a range of, let's say, these days half kilometers, maybe 2, 3 kilometers, depending upon the 700 megahertz, 2.4 gigahertz you use. So in 1 kilometer, having 90,000 people is rare, or 90,000 subscriber concurrently requesting something at the same time is rare. Okay. So yeah, this is like a hello world application. You send, actually not hello world, let me be correct here. Hello world here means that each of these user is sending their CQI, buffers, backlog buffer, RLC states, and several other identifiable, roughly, let's say 1 kilobyte per user. So it's sending 90 kilobytes uh, through this tunnel to the other side, and then getting those response back for those 90 kilobyte. Hey, we got that 90 kilobyte successfully. That's the precise measurement being done here. Yeah, because I think this is x86, right? There is no guarantee, even after you locked threads to particular core and whatnot, no guarantee on uh, how it takes variable times. Sadly, yeah, there's like, yeah, very hard to. This is the entire problem with the x86 is this, right? Like there is no guarantee on the computational time, right? So this is why everybody wants to do FPGAs and whatnot, right? As you know, right? So this is why I guess CDFs, right? And yeah, we did all the nice things you would like to do. Typically, what you tend to do is that you take a core, you assign the thread on this particular core, which is going to just do exactly this. And then in this also you do some kernel level optimization that this will do this and that and so on and so forth, right? So after that, we sort of get these numbers. Yeah. Okay, I think let's get to now the key thing I want to impart today is following, right? Okay. So now that we have this platform, right? How do I develop ML AI algorithms, right? How do I train them and how do I test them? So I'm going to focus on these 3 questions, right? Okay. And more importantly, I will give you a recipe to doing this, right? How to do this with EdgeRIC. And I'll try to very, very quickly go over all the other security and other things as we have developed, right? This actually we learned really the hard way, this part. Other part was relatively easy. So let's see this exact problem of QoE optimization, how we can achieve it. And interestingly, it was not. So let's take an example now. So RL, we are trying to use a reinforcement learning model, and the idea is that a UE with a YouTube, we are trying to use that and minimize the outage events at that UE. Okay, right? And this is where we are trying to use to have a reinforcement learning model which takes the RAN state, application state, and application state is just precisely the buffers, right? RAN state is everything from CQI and whatever the RAN dumps, we get all of that, right? And based on that, we take some actions, and these actions are provided to the RAN stack. Now, the interesting part is that the information from RAN stack comes at sub 100 microseconds. However, the application client and application state is very slowly changing. So this is why having a large delay from application client to get the application state on the EdgeRIC is not a big problem. It's, I think, an interesting empirical understanding. Application and their states changes very slowly on the order of seconds, but the RAN and its channel changes really, really fast. So EdgeRIC by itself is like a very simple innovation in some sense, right? Just like looking at some of the obvious things and defining the right latencies. And then once you have those, the training these models will become relatively easy, which it was. But still, there is a lot more challenges on how do you do it, right? So this is where we are trying to do is that the the reinforcement learning models are continuously being trained in the background on near real-time RIC. But once a model is trained, that model is deployed for inference on the real-time RIC. And this model takes these information and it provides weights. And these weights, in our experience, achieve pretty much the same thing we would want to achieve by just doing RB allocation. Okay. Sorry again, I think. Sorry, I think this is becoming harder to control. I don't know, something. Yeah. So let me go over with one simple operation, right? Okay, so that it's super clear. So RAN sends these metrics, right? And often these are RNTI, CQIs, backlog buffers, and it maintains the history of those in the EdgeRIC, right? All those are then provided to an EdgeRIC policy computation. Let's call it some reinforcement learning model and its computation. And those informations are sent back and then RAN here implicitly in the MAC layer picks up whatever weights it has right now, latest weights, and it does a resource block scheduling on the RAN side. So this operation of the RAN is perfectly decoupled from the operations of the EdgeRIC entirely. Okay. And now this keeps on repeating itself, right? Okay. So 2-3 points I want to highlight here. One, these two systems are asynchronous. This system, whenever next tick comes, TTI, it dumps all the information. And EdgeRIC also independently works itself. It picks up all these information and computes new weights and deliver those weights. Those weights are next asynchronously picked up by the next TTI or in the current TTI, depending upon whatever state it is. Now, one TTI delay doesn't affect our problem or us right now. Okay. Hopefully this is, so there was an interesting synchronization problem. We broke that synchronization problem by just saying, we will just do some time states here and there. Okay. So this is what the CDF looks like right now. This is with reinforcement learning and all of the computing we kind of take 0.1 or 100 microsecond for the entire computation, 60 to transport and maybe somewhere around 30-40 microseconds to compute this policy. An interesting thing is that this entire computation is taking place on CPU, no GPUs. So we don't require at the DU to have GPUs. Actually, it's very funny. Inference is almost always, at least reinforcement learning based inferences are very, very small compute. You don't need GPUs. Only for training, maybe you benefit by using GPU. Here, the problem was taking the data from RAM to the GPU itself took a long time. 50 microsecond was spent just taking data from RAM out to the GPU and then computing on it and then sending both those decisions. It just didn't make sense to do anything on GPU for this because the model was very small, right? And yeah.
But they run some of the AI apps on those GPUs so that it hits it directly.
Yes.
Can it be used to optimize?
I think so. Yes, you could. Yeah. Yeah. We actually haven't tried that though. Yeah. 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 But that could be an interesting thing.
See, they will try.
Right. Yeah. I think there is one model which is right now very heavy, which we actually, instead of running on the EdgeRIC, we ran into on the near real time. But that might be which would benefit with this variation. Yeah. 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 For sure. So, okay. Now, look, the reinforcement learning algorithm and the Q learning and the variant of what which we used here, and all of that is very, very good, well understood knowledge, right? Okay. I'm not gonna, like, I think the problem with the reinforcement learning is training it reliably, right? And why it's hard to train it reliable? Let's think of it following. If I try training an online reinforcement learning model, here is the problem. I have no idea if your model you're trained is doing better over time or worse. You want some form of repeatability with reinforcement learning. At least in the case of wireless, we thought it's important, right? Because we were continuously training on real world data. As soon as like you start up a base station, you start training your reinforcement learning model, everything is happening online, right? It just, you never know as you train it, it's getting trained and getting to better optimization point or not. So this problem is when we sort of realize we need something where we can do some repeatability. Reinforcement learning model, you want to actuate with same state or same events, and there is a lot of cascading which takes place. If you took a decision wrong at time t, it might affect you at time plus t plus capital N, right? You never know, or you never understand these if you cannot do something repeatably. And doing real world experiments repeatable is impossible. You cannot do it. Like even if you create same environment, same everything again and again, you will get very different results. So we were having very, very hard time training an RL model in real world and then using it in the real world itself. So it's like, imagine you train it for 1 second and then you use it for next 1 second. We didn't have any good luck on this, right? So we went back to, okay, can we use a lot of simulated digital twins for training it, right? Okay. I'm going to go a little bit quick. And how we obtain data is that we used uh, lots of outdoor test bed, right? Okay. We also used indoor test beds, right? And so the digital twins we created, we used wireless inside. I'm going to show this quickly a little bit. You create a 3D graphics model, right? You can use OpenStreetMaps or whatever for the environment, right? You instantiate different base stations, different users, you create different channels. And once you have all those channels, you can take these channels, make sure they have spatial and temporal consistency. Funnily, 3GPP channels don't have spatial and temporal consistency until very recently. They just recently, after we told them, they have started adopting those into their, or 4 5 years ago, they started adopting these things, right? They would simulate a channel and they would just use it for some MIMO related things or some of the other things, right? They were never bothered too much about the spatial and temporal consistency. But when you're training and reinforcement learning model and trying to learn, this starts to matter, or your model doesn't converge if you don't have these behaviors, right? And then on top of that, we were using these stacks, Open RAN and SRS RAN, right? Okay. So an example of this is that we have a car moving on a street at UCSD. We instantiate a base station and we collect lots of traces for that car moving at different points in time. Same thing, we do it with extensively with wireless inside. Now, we realize if I trained a model entirely on the digital twin, what's great about digital twin is that I can create same setting again and again and again and again and try training my model and get to a convergent point. It does converges, right? And you can see the policy, it makes sense, right? When you plot different CQI to backlog buffers and you show different UEs who are competing, you get a real good deterministic behavior, but it doesn't translate. So then we went on to collecting a lot of channel data set with the same settings of users moving and other things, right, in the real world. Instantiated base stations, SRS RANs, collected similar logs, right, and understood the real world channel really well. This is both for FR1 and FR2. FR2 we don't have. I think we realize it's not that exciting or interesting. It just nobody wants it either as well at this point. So we created a large data set which has both simulated and real world. So we use simulated to get to a slightly closer point of convergence. And after that, we fine tune using the real world traces to get to a better point. Now, the second point is that even with the real world data set, right, we keep running the same model again and again to get repeatable measurements and understanding that the model has trained to a point of where it can converge really well, right? Now, all these channel data sets and emulated base station and entire emulation, this is available for you if you want to try it out at edgeric.github.io. So go for it, go try it out, right? So some of the, so now this is more detailed diagram of how you do this emulation. I told you that you can do an entire emulation. And this emulation, by the way, for us takes place in the near real time all the time, because that's where we have lots of compute. This requires a lot more compute for training, right? Because we are emulating the entire base station, entire users and all of this, right? It takes some amount of resources. So this here's what the emulator looks like. You have application client, TCP, UDP, 4G, 5G core, the RAN stacks you're using, right? And the ZMQ with the EdgeRIC we have, right? And you instantiate this entire thing as one container or multiple containers, however you want, you can do that. All of those are supported. This, instead of doing over the air transmission, the IQ data is taken over and channel for each user is applied independently, and that channel then essentially feeds into the user and its application. So with this, you essentially can create the RF without the RF, but you can also guarantee repeatability. You can run same application clients, same everything, keep running again and again, again and again until you see that you're starting to see a better perform or improved performance reinforcement learning model is built or not, right? So these are some of the real world traces. We have a drone, we have a car, we have some turntable, just small user mobility, and then there is a mobile robot, right? And some of these are at UCSD, some of these are at TAMU, and we collect lots of these data sets at different locations and try training models based on that. Here's a video for EdgeRIC. So the cool thing I want to show here is that how agile it is to change the scheduler in runtime. So we have a base station, 2 user, the setup, right? These are standard USRPs and you can easily set them up, right? So we are doing some standard iPerf based downlink and uplink test, and you have different iPerfs on different users, total throughput, and so on and so forth, right? And it keeps showing you current scheduler, right? And on the EdgeRIC side, you can easily change these schedulers, right, by just with like typing a command. So in real time, we showed if you give half, and then there is a, this is PPO with initial model, which is the reinforcement learning model, right? I think PPO is the standard algorithmic way of, any case, it's fine. So now half trained model is deployed, you start seeing throughput improved, right? And then we'll have a fully trained model deployed. Again, these are getting deployed in real time, right? Literally, as you get trained, you can deploy them very quickly, right? So the point I want to show is that this is a very cool platform and it has high agility. You can instantiate, you can run it to some real users and create some real traffic and do whatever experiments you want, right? Again, it just keeps goes on loop, right? You can even load some CQI traces and do layer 2 only experiments, right? I'm gonna skip this. This actually was a very interesting result. So now we have created this digital twin, right? How representative is this digital twin of real world? Okay, so imagine you are now coming up with a new, some form of a Discord, right? Everybody knows Discord. Most people know Discord. Okay, all right. It's just sort of a like Zoom or Teams, right? Just for gaming, right? It has some gaming related advancement and a lot of gamers just use it, right? And it does optimize broadcast audio and so on and so forth, right? Now you want to test if you can use the same broadcast app slash whatever you're building and what is the performance you'll get. So here I'm showing jitter. Jitter is one of the key metrics in the video delivery. Okay, it's also one of the metrics which is hard to optimize when you do QoS optimization. Okay, so what I'm showing you is that in real world, what you would see on a network versus what in our digital twin we see as a network. It's not exactly same, but it has one interesting feature is that whenever there is a minima on this one, there is a minima on this one as well. That's as far as representativeness goes, right? Now, number wise, definitely there is a difference. Instead of getting 5 millisecond in your simulation, you get somewhere around 10 to 12, right? But it at least tells you which is the point which you should operate at. How should you do configuration optimization for a purpose-built network? So this was a side benefit we realized of our digital twin, right? It's close, but it's not exactly same. Okay. So we trained our scheduler on the digital twin side of things. It does decent training with training iterations. Around 40 iteration, it starts to converge. Once you plot the model which is converged and you have multiple competing users, you see it's doing decent stuff. It's understandable stuff, right? And then we actually deployed in the real world and we saw the same throughput. It pretty much got right result. Max weight is supposed to do throughput optimization. Reinforcement learning does same as this, right? If anything, it has slightly larger variance. And I think we still, maybe just, it's still not as good model as we were hoping, right? Okay. But it's good enough to have similar like median performance, right? So max weight is supposed to maximize throughput just so that it's a standard scheduler out there, which is supposed to maximize throughput. And it also achieves the same thing. But look, throughput is not the point. The point of all of this 5G is that I want to build a purpose-built network. Can I do QoE optimization, right? So that was the next thing. So now we have 3 users. 2 of them are streaming 2 different videos, and one is just downloading a large file. Okay, this is called as EMBB class of traffic roughly. And if people know this, right, it's okay. So now we trained again different reinforcement learning model with similar philosophy. We have CQI backlog buffers, right? We have application state, which is media client, and you get every 30 millisecond a packet. And you train the model again with the same repeatability digital twin we have created, right? All the cool stuff, right? And now we benchmark the performance over the air setup, right? So we are trying to measure stall duration. This is the stall performance I showed you earlier as well in the graphs. So we see roughly 2 seconds of stalls created in total by EdgeRIC / the reinforcement learning model on EdgeRIC. Then max weight and max CQI, these are in-stack schedulers, right? We tried different combination and permutations. None of them beats us, right? And we get significant performance improvement. And this is entirely of what I discussed earlier. Knowing when what is going to happen has significant improvements, right? Okay. Now, one might say that I am doing an unfair comparison, primarily because max weight and max CQI do not have application state. But my entire point is that application state is truly powerful thing, and that is what you need to do that optimization, right? And none of those optimization you can do in today's traditional stack. Worse yet, we have a similar graph to show if you did the same reinforcement learning training with the near real-time RIC, which has a lot of delay, this definitely I can show you those paper exists. The paper has those results, but they also perform at par with these max weight and max CQI because they are pretty much out of sync. Near real-time RIC has so much delay in knowing the channel and understanding the channel that by the time it comes back with a decision, it's already outdated. It's not useful anymore, right? And it tries to learn how to predict channel 10 time steps or 10, 20 milliseconds in the future. It doesn't do that well of a job to learn these things. These are high mobility in uncontrolled, realistic environments, right? So it fails basically. So we get significantly enhanced QoE, right? So this was sort of EdgeRIC, tiny twin. Now there is another application where you have a jammer. It's security application. We want EdgeRIC to provide beam arming, right? You have multiple antennas. You arm yourself such that this jammer is not effective anymore. Okay. So can you create these nulls? Again, it's not that hard as a technical problem goes, but it's what is exciting is that you can do this in a matter of hour with EdgeRIC. If you had to write this entire thing from ground up into a RAN stack, it may take months to just understand where to get channels and then where to apply the nulling and how to apply that nulling. All of that gets simplified with EdgeRIC. Actually, we got, like roughly speaking, 5 crores to do this, right? And it took us 1 day to do it, right? Not to just to give you a sense, because only we can do it, right? Okay. So that's what happens, right? Anyway, so this actually happens in the real world as well. In cellular, you use FR1, frequency reuse 1, right? Therefore, even a nearby base station can start acting as an interferer to you, right? And you have to deal with the same problem. So this problem is both DoD plus a commercial use case, right? A dual use problem, right? And there are lots of other RAN controllers and whatnot, right? And not a lot of which can do MIMO applications and millimeter wave applications. Okay, so this is our first one. We call it MIMO RIC just as a new branding, right? Okay, but same thing. It's EdgeRIC, but just does really lots of MIMO related cool things. Yes.
So, I
Yeah.
Karen had said that they are
Yes, they keep saying that to me for last 1 year. But yes, please continue. So we actually are working with them right now. So they actually even built a patch for. Actually, we had to sign some number of NDAs, right? But they have given us some early version, I can say that, right? And we are trying to work with them and build or transport all the apps we have built to Janus as well. Or we are also evaluating, can we just take, because Microsoft is building it and maybe just they will continue to support it, we'll just build EdgeRIC on top of that. And that way it's more better engineered rather, let me put it this way, right? Okay. Yeah.
Mosaic and web series.
Yes. They are. Yeah.
The tiny twin is about the digital twin project.
Yes, yes, yes. I just call it tiny because it's relatively tiny, right?
Because did you when you're developing the tiny,
Yeah.
consider the Maverick because Maverick is also designed for big algorithm development platform. That's what
Right,
they call
right.
digital twin platform for developing bricks.
I see, I see. So actually, when we were doing it in like 2-3 years ago, this right, I don't think I knew of this Maverick Rick, right?
It's on Facebook.
I see, I see. Actually, they disbanded this project, right? If I understand correctly, still continue? Okay, I don't know of it. Actually, to be honest, I don't even know right now about this. So it's good to know. I think that's exciting. I think our more important problem was anything we use, any model we trained, when we actually deployed in real practice, none of them worked. That was our big problem. So, and the only solution to that we realized is that you use all this simulated data to get to a decent starting point as a model. And then you use real traces to get it to a better point and better performance, right? I guess maybe let me put it this way, right? It's sort of when you train these in emulation, simulation, right? Um, the channel representation you kind of come up with, they are very hard to be accurate to the real world, right? And since they are not accurate, you might be learning some constants or some number of things which are not as representative of what the real world is, right? So maybe our fine tuning and fine tweaking, let me do later on, sort of fixes some of those problems. Actually, we have tried looking at the models and comparing the outcome and plotting the results, right? You can create two user traffic and then try to compare the decisions it would make, the trained model, and compare these two trained models, right? We see lots of differences in these two models, right? The point at which they have some minima slash local minima behavior versus points at which they have local maxima and so on and so forth. They are very, very different. So it's very, actually, to be honest, I don't think, I was hoping I would get a better insight by comparing and be able to say that this is what is broken in the simulated models, right? I don't think I have answer to that, right? Like, I think if you have a trained model on simulated and in real world, and then real world is working and the simulated is not working, can you say something back about what is missing in your simulated channels? Yes. Yes, I think we have been experimenting with some of those. I think to me at this point, okay, what is the next important problem should I be solving, right? So some of the problems we are right now looking at is that when I have multiple applications with multiple application states, what do I do? Can I still generalize this model? This is a real important question. I think algorithmically, I have to say that this worked well enough that we didn't bother with some of these other ideas. But yes, I think once I start looking at this problem, which I'm just talking about, there we are right now trying Whittle index-based networks, right? I think those seems to be giving us some promising results. I'll get to that as well in a minute, right? And I think how are we doing on time? Sorry, we are far above the time.
That just I know it's
Sure.
maybe the Nokia interview, which you use that trick.
No, I think we have tried getting a black box version from them so that we can compare, we can run the same stack on the same radios, right? Once we run this experiment, once we run that experiment, and we can compare. We haven't yet gotten access to those RICs to compare it.
Yeah, we're doing the overall estimate.
Yes. So actually, this is Nakjung and Ahan Kak, right? Who these guys are sort of taking OAI stacks, and then they put it together with OSC RIC, is my understanding.
They have
Yes,
mosaic rig.
Mosaic or Flex RIC. Any case, whatever the name be, please continue. Yeah.
Yeah. No. So they have Oran SC is from Nokia. Yes, right. The Oran SC.
Right. Yeah.
So
And so what I know is that Oran SC's RIC, Nokia guys itself integrated into OAI.
yes.
And
Of course, yeah.
that we were hoping to get that version for us to compare against, right? And see if that does any better, or like, I think it's a very, sure, for sure. So I'll make some quick points on MIMO apps, right? You can build a lot of intelligent things, right? Okay. In no way I'm saying I'm doing anything intelligent right now. I'm just saying I am giving a platform which you can build on MIMO, on which you can build MIMO apps. And one such we think we did build it, right? I think it just shows how we can do beam nulling, and it requires only like a 7 line of code to do beam nulling. Okay. Again, we are also right now building a OAI plus FR2 code base, right? Okay. But let me just go. So this is what you want to implement. Roughly speaking, this is a beam nulling, right? With your Y star, right? Okay. And it's a simple formulation. It's not really scientifically exotic, right? Okay. But building this took like 10 lines of code. I don't think I have that code in somewhere. And this is the demo for it, right? I think I'll show the videos later on, and it works, right? There's not really mystery there, right? But here's another multi-site. So this is the other problem. So once you start putting these things on edge, how do you scale it to multiple site becomes a real problem, right? And that's where truly the heart of it is. So here's a use case. We have 2 radio units. One radio unit or one site observes an interference in this band. Okay. Another site observes an interference in this band. Okay. Let's just say it happens for some reason, right? These are 2 sites, 2 DUs, and 1 CU, and so on and so forth, right? Okay. We built EdgeRIC. We showed that EdgeRIC can manage these multiple sites and can do different spectrum distribution, and that way you save the energy you transmit, right? Ideally, what you want is that you want this site to just use this part of the spectrum and this site to use this part of the spectrum. The good thing is that if you have that part done, it's sort of like interference management in the Wi-Fi / it's interference management in cellular. You don't spend your power on the spectrum where you're getting interfered with, right? Okay, that way you save your power, energy, and lots of you do spectrum efficiency and so on and so forth, right? Here, this part required a lot more resources in terms of training and detecting interference, because you are using slightly like heavy techniques like ResNet, where it was doing image-based analysis to identify what is anomalous, right? And therefore, we had to put this in near real-time RIC. And this is the overall diagram of this, right? Okay. That the spectrograms are carried into the near real-time RIC. We do interference detection. Once those interferences are detected, EdgeRIC is informed about what interferences exist on what base station, and then it essentially blanks out the other resource blocks, right? Okay. Simple application, but the key idea really here was to demonstrate, does EdgeRIC scales to multiple sites, right? Okay. And it does, right? And this is now also accepted to some census or something will be presented in a few months, or actually CONEXT, yeah. Okay. I think some results for this. Let me go to one interesting work, and this is actually even done by former IISc student, I think, Archana Bura. She was here, I think, with somebody. I don't remember exactly. So she has been working on building something called Windex, where how do you do QoS with constraints? Okay. So the idea is that, look, people want to do QoS, and I also want to do QoE because it helps my users. And if you try to create this joint formulation, it turns out to be a constraint reinforcement learning problem. Okay. So you have QoS, right? And you have to meet these constraints which are dependent on QoE, right? Okay. And we have a slightly interesting formulation for this as well, right? Where we are using Whittle index based formulation to sort of do some of the decoupling. right? And in essence, what we do is that we put constraints on throughput and latency. Those becomes your QoS constraints, right? That's what you use to sort of define QoS, right? And then QoE is your sort of actual optimization function, right? Subject to these constraints, right? And then we do scheduling by using Whittle index concept, where we try to create a nice decoupling between these two problems of constrained RL. And then again, this is a very interesting paper to read. And the idea is that you have a Windex network which takes all these violations, which are the QoS requirements, and the other input information we had even in the previous model, and we create some Whittle indexes. Those Whittle indexes are then given to a Whittle scheduler, which essentially gives you different weights finally. Okay, this sort of allows us to meet QoS plus do some QoE optimization as well. Okay, hopefully this is clear, and it's actually very nice theoretical problem, which if you're excited, you should go read this paper and you can follow up on this with different models and different things, right? But this is, in any case, I'm going to skip some of these slides. It works. Okay, again, look at the paper. So just to give you a little bit of uh, what's next for these EdgeRIC slash real-time RAN intelligent controllers, right? So this is where we had a 2021 proposal in 20 this. We pitched to Nokia, we pitched to everybody else. They have been building their own variation. Northeastern built DApps, something on similar to our variation, right? There is Janus, Decima, TinyRIC from Nokia. This is what I was talking about earlier. Again, some variations of this, but overall the point is that everybody is realizing that we need some real-time decision making, okay? And if you are looking for a topic or a sort of a area to sort of focus on, right? I think start doing real-time intelligence, right? I think it's exciting area, lots of interest from lots of entire community and standardization, and everybody's coming around to this idea, right? Okay. I guess lots of people are using it. Feel free to welcome to join. These are some of the applications I showed, right? So let me summarize two messages, right? One, like real-time RICs are really powerful. Two, we have given a recipe for how do you take or how do you develop ML training and deploying that ML models, right? This recipe is hard learned, right? I think if you try doing today, you will go through the same set of problems. Instead of going through the same set of problems, just follow our recipe of training the models and deploying them and seeing if they work or not, right? Okay. And yeah, with that, I'm happy to take more questions now. I can show you more videos. There are like lots of testing facilities we have at UCSD, right? 10 plus SDRs, all of them are connected to a rack of servers, right? You can do whatever you want, deploy lots of containers, Dockers, right? And this is also has OAI. We have connected this OAI over internet to from East Coast to West Coast. This is connected between UCSD to NYU, right? And this is the Internet 2's infrastructure. UCSD has a supercomputing center. We are co-located with that supercomputing center, and that's how we have a 400 terabyte link all the way to NYU, and we do, it's like our own internet, right? We work and we decide who can do what, right? Every single switch we can control and do whatever you want. Okay, so this is where we are today. Yeah. Yeah. Sure. Yeah. Yes. Why? Right. Right. Yeah. Yes. Right. I agree. No, I think so. The way at least to think about it is following. Actually, I think I should have gone through the Windex a little bit carefully. Let's think of bearer in the following form. Bearer is application and the UE, and its matrix grid multiplication is each individual bearer. So let me explain. One user with video traffic will have a different buffer of its own. One user with audio traffic will have a different buffer. So all of these are different competing buffers now. And now I guess there is a slight intricacies that because I treat them now, think of these as UEs. And I am deciding which one to should get DQ'd amongst all of them. Yes, and how much, right? And I'm assigning weights for those as a bearer. I don't make a bearer with one UE with all types of traffic as a single bearer. Okay. If I do that, then that the problem you just made or argued for, you won't attain the most generalized form. With this, I think, does that address your question? Basically, it's not automation. I agree with that. The, that's take care of all the variety of traffic. And I need to be able to address sometimes I see the run multiplier. Right. That's one thing. Second thing is that any given traffic, whether it's PQ or whether it's non-station. Right. Non-station. Right. So how do you good question. Fair question. Right. So I think you're getting towards the second element of reinforcement learning. So I've been telling about this near real-time RIC, and it has in the background is continuously training a new policy. So the deployed policy on the EdgeRIC is not updated as often. Okay. But as and when we notice that the distribution has gone off from what we have actually trained for, right? Then we take the we keep continuously training the RL in the background on the near real-time RIC. Slightly delayed, but it keeps continuously updating itself. Whenever we see we are off, we deploy that policy, the new policy which has been trained, right? And then we start using that new policy, right? So it's sort of a cheating in some sense. I'm not arguing that I would learn a most general form of the model. I'm just saying, as you said, in that realm of time scale, if things and events have changed, based on that, I would learn something new and then deploy that something new. So yeah, hope that addresses hopefully your concern. Yeah. Yeah.
Let's all come to the speaker.